So up to this point we have created the layout and saved the design. Now we have to go for DRC check. Before going to DRC check, first refer the tool that which technology you are using. In our design, we have designed our file with 90 nanometer technology. So the file which you need to attach is Ashura Tech file. In our system, it is available in the directory root Cadence tools GPDK. That is, these are the three technology which are available here, out of which we are designing our file in 90 nanometer. So if you go for 90 nanometer, you will find a file named assuratech.lib. You can choose that file and give OK. So the path of the technology file will come here. So we have given the technology file name. Now again come to Ashura, run DRC. Initial setup, you will have technology to be undefined, and this will be your library name, cell name, and the view is layout. So now we need to define the technology, that is the 90 nanometer. So if you could click on drop down, you will find the technology file which you have just attached, that is 90 nanometer GPTK 90. Once you give the technology file, it will take the DRC rule part automatically, that is drc.rule. So now we are going for DRC verification. So I want to view the DRC result. Okay, so here is my error window. There are three errors. One is P implantation area should be more than 0.15, and N implant and metal layer. So if you click on AV, then go to layout, then click on zoom button. Other time it will highlight what are the errors. One is this distance should be more than 0.12 U, and this width should be greater, that is it should be at least 0.15 UM. So now in order to check the sizing, you go to tools, there ruler will be available. You can select ruler, and now let's see what is the size currently available, that is what is the distance between these two metal layer. It is around 0.9. So we need to move a bit so that it becomes more than 0.12. So I am choosing the stretching tool, selecting this and moving to the left. So I have moved the metal layer. This is one verification, one error rectification. Other is we need to increase the width. Since the MOSFETs have a minimum width, the default symbol which is created by Cadence is not, that the size of implantation is not according to DRC. So we need to increase the size of implantation. But since if you press only Shift and F, it will not give access to the internal layer of the mask. So in order to access the internal layer of the mask, you click on the symbol, because we have to increase the size of the P implant. That's for that first we need to have access to the layers. So select the symbol, layout, mask, go to edit, hierarchy, then choose flatten. Here enable flatten P cells and preserve pins, then press OK. So now you can see that it is flattened and you have access to the internal layer of the masses. See, I can click the layer separately and see what layer it is. This is the oxide layer. So if you go to property of that layer, by clicking on the I button, it will show you what layer it is. See, this is oxide layer, and if you come here, the next layer, this is an implant layer. So we have error in this implant layer that should be maximized. Likewise, you can check the other layer details too. So now I am trying to increase the area of the end implant. So I am choosing the stretch button, stretch function, wherein I'm selecting the P implant alone, the N implant alone, and I'm stretching it to the left side. You can see that the area has been increased now. P implant N implant area has been increased. That stretch you have to choose from here, this button. That will be even available in the edit menu. So now that I have did for P mass, now I'm coming to N mass. Same, this is oxide and this is P implant here, and I'm again choosing the stretch button. Okay, see, now we have not flattened it, that's why the internal layers are not getting selected. So I need to flatten this first. Edit, hierarchy, flatten, both are checked. Press OK. Now I have access to the internal layer. Now I can come to stretch. So I'm stretching it. Actually, you can calculate the area and give an exact area here, so that it is 0.15 um. Now I'm saving the design. So after saving the design, I'm again going for DRC check. So Ashura, run DRC. Okay, because already the technology file is defined, so I'm just directly running the DRC check here. I'm viewing the result of DRC. I can say that the DRC error has been rectified, so no DRC errors found. So you could see that what are the steps we have did till now is, first we have created the schematic, 2 we have created a symbol, 3 tested the symbol, 4 we have created the layout, 5 we have passed DRC check. DRC, and fourth step is LVS. LVS in DRC, the tool will just make sure whether the layer sizing is dimension is according to DRC rule, but it will not see the connection between the pins. In LVS, the connection between the pins will be checked. That is, it will extract the layout parameter as well as schematic parameter, and it will compare its results. So for that, you need to go to Ashura, come to run LVS, and again here you see technology. This is a part of your schematic and this is a part of your layout. So these two are going to be compared, and technology you choose GPDK90. So this file will be automatically loaded. So now I am running LVS here. Okay. So now it is showing few warnings. Multi-label GND. Okay, GND ground. With respect to ground, it is showing warning. we are debugging the error now. Short locator, body tie left and B is shorted, it is saying. So we will just draw a line of flight. Okay. So here it says that these two are shorting. In according to schematic, these 2 points should be shorted, but still it is showing error. Let's see what is the mistake we have. We can see that this node, that is source of NMOS, that connectivity is ground, just given ground, and see bulk connectivity, body connectivity, it is B left, it has came. So but it should be actual ground here. So for that, here in the terminal name you can change it to GND, click apply. Okay. Cannot change terminal ground to ground already existing, but also so for that, what you do is, this should be ground. We will delete this layer and again we'll copy this, that is this pin is ground pin, so both should be ground actually. So this is defaultly ground, so I will just copy this, put it here. So now both are ground, it is connected, and then let's again go for LVS. See, these errors were not notified in DRC because it was just checking the dimensions rule alone, but in LVS it is checking connection between the schematic and layout. So now we have got that there is no, it is all our mismatching, so there is no mismatch or warning here. In the next window you can see that it is notifying us schematic and layout match and extract, no extraction warning nor error has been detected. So now we can say that we have passed LVS here. The fifth step is we will go for RC extraction. RC extraction. So for that step, you again go to layout. Yeah, here is my layout. So in the RC extraction, we are going to extract the resistance and capacitance between the interconnects and the between the layers here. So for that, I need to go to Ashura. Here run RCX. In the RCX, make sure the technology is GND, that is GPDK 90, and the output should be extracted view. Defaultly it will be SPICE, you should change it to extracted view. And here come to extraction. Extraction type is we are extracting both R and C here. So give R and C. Now that we should fill the reference node here. Reference node is the lowest potential node. In the schematic you can see that lowest potential node is GND here. If you have used VSS, then you should type VSS there, but I am typing GND. Okay, now I am going for RC extraction. So it is saying that extraction has been successfully completed. So we have finished the fifth step, RC extraction. Now sixth step is creating a config file. Config file will help you to simulate your design both in schematic mode as well as in the layout mode. whether the simulation is to be done over the schematic or over the RC extracted design, layout design. So I am closing the layout as well as the schematic now. Coming down to Virtuoso window. Herein I am opening the symbol which I had created to test I am opening the file which I had created to test the symbol. So open GR library. Here you can see that now in John Inverter you can see 4 views are there. One is schematic, symbol, layout and AV extracted. And this was a test which we created, test file to test the inverter. So that is only in schematic view we have there, because we didn't create layout or we didn't go for AV extraction there. So I am opening that. You can see that this file is in schematic mode. Now we are going to create a config file of the same name. So again go to file, new, here library choose, this is GR library, and the cell name should be same name what is given here, that is inv underscore test, and type should be config. So now we are creating a file, config file for inv underscore test. That is open. It is only one option we have, that is hierarchical indicator. Go for OK. Now a window will open wherein we have to set up the configuration mode. See, these are the default setup, and view you need to choose schematic. In the drop down you will get schematic. Yes, choose schematic. Now go to template. Since you are simulating schematic, you need to go for spec tree. If you are going for mixed signal, then Verilog A will be going, but since it is schematic, we will go for spec tree. It will take the file automatically. Click OK. So these things will come default setup. Now that we have created the config file here, now just save the config file. You can see that we have created a config file. Nothing. Now I am going to open the config file. See, to open the config file, again I can close the schematic for now. So I'm going to open from here, file, open. So test, you can see that we have got a config view here. So browser, the editor, click OK. Now that you will get a two option. One is in configuration mode, we need to edit the configuration. So click yes, and top view will be of this name. OK, both should be yes, selected yes. Now OK. You can see that here we have a config. When you click yes, we get a two window. One is hierarchical editor window, and other is schematic window. You can see that here it is in config mode. Previously it was in schematic mode. Okay. So now the schematic, this is the symbol which we have instantiated here. These are the masses available in the symbol, and these are the sources. You can see that if you right click on the schematic, that is John Inverter, in the set cell view you can see the AV extracted view. This is the extracted view which we will use for post layout simulation. Now that it is schematic, we have to save the design, and now I am going to the schematic. From schematic I am going for a transient analysis. So I am choosing the analysis type to be transient. Our period is 10 nano here, so I am running for 20 nano, and output to be plotted on, outputs to be plotted on output, and the input. So now I'm running the simulation. Fatal error. Let's see what are the library files we have in the setup. Go to setup, model libraries. See here we are using only 90, but we have got 45 and 80 on the stack, so we need to delete these two libraries. We will just have 90, that is 90 library alone, GPDK 90. Now run the simulation again. So this is a simulation result which we have got. For the schematic, I'm expanding these waveforms. We'll just make a note that this output belongs to schematic simulation. So I'm going to write here output, just for reference, is CH schematic. Okay. Now again go to hierarchy editor window. Here now the inverter I am choosing that to be in AV extracted mode. Previously it was schematic. Now, yeah, before that, make sure when you go to tree view here, when you expand the inverter file, you could see only two MOSes are there, NMOS and PMOS. Now come to table view, choose AV extracted here, view, and now save it. Again come to the tree view. When you see in the library, you will find capacitor and resistor additionally. Those are the capacitor and resistor because of the between the terminal or between the layer. So these are the parasitic capacitor resistors. So now you can see that here we have AV extracted view. That means that the simulation, whatever we are going to perform over the schematic now, it will be post layout simulation. So again I am coming to the ADE window. Here I am appending the results so that we can see the difference between schematic result and the post layout results. So append, I am plotting only V out here. So I can see that here this is out of schematic and this is V out, which is post layout simulation result. I will change the color so that we can understand the difference. So these two are different color. So let's zoom in the schema waveform. Here you can see the difference. It will change the style of waveform. Yeah, solid. See here, actually this is out of schematic, which is responding faster, the maroon, and what color yeah, the other one, post layout simulation result, it is responding slower. That means that because of the parasitic capacitor resistance associated with it, it is responding slower. Again, this is a falling edge, and now we are coming to raising edge. Even in the raising edge, it is same. You could see that schematic is responding faster compared to post layout result. So now here we have opened the config file, and then we have ran simulation over schematic, and then we have went for post layout simulation. So we can see that these are the difference between schematic simulated inverter and post layout simulated inverter. Thank you.